into the count yesterday, but encountered unusually high upper-level winds, which affected the debris corridor. In the event of a flight mishap, there's a specific debris corridor that needs to be maintained, and those high-level winds were in violation of that. So that brings us here today for another attempt. The team is well into the count today, and as you mentioned, we just finished the polling for main engine chill.
And with that, we're just looks like the clock about 25 minutes or so from launch. So one of the was talking to John before we went on the air, and the exact same launch team is on consoles there at Wallops Flight Facility supporting. So Adam Lewis is the voice that everyone's going to hear as part of the countdown through liftoff, as he is the launch conductor.
That's correct.
And then after liftoff, we should hear Mike Dorsch, who is the Antares chief engineer. So those are the voices that you'll hear, among other flight controllers, here and there through the last few minutes here of the countdown.
That's correct. Frank Culbertson, our Executive Vice President of Human Spaceflight, is the Antares launch director, mission director today, actually mission director. Kurt Eberle is our launch director. And we have a supporting team from NASA. Sarah Doherty is the NASA technical director today.
So everything continues to go smoothly, again, with this test flight, which is the first of two missions that Orbital has scheduled to conduct this year under NASA's Commercial Orbital Transportation Services program. And the next few steps in the countdown, the next major step will be a poll to proceed with the final countdown. That should come around the 12-minute mark before launch, so about 48 minutes after the hour. And then that will lead to the start of the main engine system medium flow chill down. That should come around 10 minutes before launch. So, but again, everything's going very smoothly. Obviously, John, with the countdown throughout the day, which of course began with the usual call to stations about 8 hours before launch, and then there's a whole series of activities that occur leading up to where we are right now.
That's correct. So maybe while we're counting down into that final poll, we could take a look at the Antares vehicle itself again. So starting from the ground up, the first stage is powered by dual Aerojet AJ-26 engines, which with independent thrust vector control. Those are supplied with liquid oxygen, liquid kerosene propellants, a total of 535,000 pounds of propellant. For the second stage of the mission, we use a Castor 30 solid motor from Alliant Tech Systems, which produces about 73,000 pounds of thrust. At the front end of the vehicle for this mission is the Cygnus mass simulator, which is protected by a new 3.9 meter diameter composite fairing. The vehicle itself is just over 130 feet long and has a gross liftoff mass of 620,000 pounds.
Teams go for final FTS power and arm command test.
As we were discussing before, Antares is a new launch vehicle that Orbital is developing in partnership with NASA as an element of NASA's Commercial Orbital Transportation Services, or COTS, program. The initial variants of Antares will be able to put about 5,000 kilograms into low Earth orbit. Subsequent versions will improve this to about 6,500 kilograms, or about 14,500 pounds.
LC, this is FSO. Wallops, primary transmitter is up. Tone 4 radio.
LC copies. FSO, check 363.
Copy that, LCA.
And Ops 2 LC on countdown 1, step 364, apply external power to FTS A and B. LC Ops 2 in work. LC Ops 2, FTS A and FTS B external power is on. And Electrical 1, verify FTS external power status.
LC Electrical 1, FTS external power status, voltage and current nominal.
Why don't we take a look at the mission profile for today's Antares test mission. The Antares vehicle today will lift off of Pad OA at Wallops Island, Virginia. At ignition, the engines start, a brief health static check is performed, and then the hold down bolts release, and the vehicle lifts off. The first stage will fire for approximately 4 minutes, propelling the launch vehicle to an altitude of approximately 113 kilometers, or about 70 miles, before separating from the rocket. The upper stack, stage 2, will continue on an unpowered trajectory for about 93 seconds, during which the payload fairing will separate from the vehicle before ignition of the second stage. Second stage burns for a little more than 2 minutes before burning out at an orbital altitude of approximately 256 kilometers, or about 160 miles. At that point, the speed of the vehicle is about 16,710 miles per hour. At a little less than 10 minutes from liftoff, the simulated Cygnus payload will separate from the launch vehicle at its target orbit.
Arm removed. Tone 4 continue.
And FTS, verify FTS arm indication.
LC, FTS, arm indication.
FSO, verify FTS arm indication.
FTS arm indication.
LC copies. FTS, verify safe configuration.
LC, FTS, safe.
LC copies. Check steps 370, 371, and 372. FTS, verify FTS SNAs and FTLU status.
LC, FTS, safe and arms are safe. FTLUs are safe.
LC copies. Check 373, Ops 1, step 373.1. Open FTS umbi loop and verify green indication.
In addition to Frank Culbertson that John mentioned at the outset of our coverage today, also obviously there's a whole host of people that are anticipating greatly today's launch. That includes David Thompson, who's the chairman, CEO, and president of Orbital Sciences, and also Mike Bitzer, who is the mission manager for the flight. Let's take a minute to hear from all three of those gentlemen.
For almost 30 years, NASA and Orbital have worked together in a variety of partnerships to develop and introduce a wide array of new launch vehicle and space system capabilities for both government and commercial customers. The Commercial Orbital Transportation Services partnership that the Space Agency and our company entered into a little over 4 years ago is perhaps the most ambitious of these joint undertakings. We are now on the verge of one of the most important milestones in the COTS program, namely the test flight of a new medium-class launch vehicle that we call Antares, that will be used together with our Cygnus spacecraft to deliver important cargo to the International Space Station and over the longer term to provide in-space logistics services for a variety of other missions, both governmental and commercial as well.
The test flight is very important because it gives us a chance to prove the entire flight system, the separation of the two stages, the separation of the payload and upper stage, and the separation of the fairing that encapsulates the spacecraft that will go to the space station. This is really the full systems test of everything to prove that when we do take cargo for the first time, that the first part of it, the getting off the ground part, really will work.
The primary objective of the test mission is to verify the newly developed Antares launch vehicle in support of the NASA demonstration COTS mission that's coming up following that, which will actually be taking cargo up to station. Then as we get closer to launch, about T-minus 30 minutes, we actually start the chill down of the engines to get them ready for launch. And then at 3.5 minutes prior to launch, we turn on the auto sequencer and turn over control of the launch vehicle. It takes us down to about a half a second before launch where we initiate the engine ignition process. Once the engines have ignited, the launch vehicle itself does a health and status check on those engines. It takes about 2 seconds. Once everything's confirmed that the engines are ready to go, we drop the hold down bolts and the vehicle takes off. From the T0 ignition to payload separation is 603 seconds, so just a little bit over 10 minutes in time.
And we're just under 15 minutes now to launch, all continuing to go smoothly. And John, this gives a opportunity to talk about I guess the big payload and the little payloads a little bit that are flying aboard Antares today.
Sure. As was alluded to in the video clips, for the test launch today, we're flying a mass simulator of our Cygnus cargo transfer vehicle. The simulator that you see there does exactly that. It simulates the mass and the volume of the Cygnus cargo transfer vehicle that will be launching in subsequent COTS and CRS missions. It's about 200 inches long, about 114 inches in diameter, and has a mass of just under 8,400 pounds, which is very close to our Cygnus vehicle we'll be flying for the first COTS mission. It's also heavily instrumented with a number of accelerometers, microphones, thermometers, and the like to allow us to completely characterize the payload environments during flight. Also on board are a series of small secondary missions, 3 small PhoneSat satellites that come to us from the NASA Ames Research Center, cleverly named Alexander, Graham, and Bell. And then one slightly larger commercial secondary payload called the Dove-1 spacecraft, which is an imaging payload.
And now let's take a look at the Ames-sponsored PhoneSats. This is a great little payload.
The Orbital Sciences Corporation test flight of the Antares rocket will be carrying a very small secondary payload into space. On board are 3 nanosatellites that were designed and built at NASA Ames Research Center, the lead center for small spacecraft development. 2 of the CubeSats are called PhoneSat-1, and one of them is a PhoneSat-2 Beta.
Someone here asked the question, can we fly a cell phone as the avionics for a satellite and have something that's very capable but really, really inexpensive? So PhoneSat was launched to try to answer that question.
Measuring only 4 inches on each side and weighing less than 4 pounds, each miniaturized satellite was built for only $3,500 each and will showcase the ability to launch the lowest cost, easiest to build satellite ever flown in space. The design makes extensive use of commercial off-the-shelf components, including a consumer-grade smartphone. Out-of-the-box smartphones offer capabilities needed for satellites, including fast processors, versatile operating systems, multiple miniature sensors, high-resolution cameras, GPS receivers, and several radios.
The smartphone vendors have put a lot of R&D money into making very, very capable microprocessors that have a lot of processing power and speed in a package that's very rugged. And we intend to fly it as a microprocessor for our satellite.
NASA's PhoneSat 1.0 is built around the Nexus 1 smartphone, while PhoneSat 2.0 Beta has improved software and more sensors. Upon deployment into space, each satellite will broadcast a signal every 30 seconds on the amateur UHF band at 437.425 megahertz. The PhoneSat project will be a success if NASA confirms reception of signals from the CubeSats. However, anyone around the world can listen for this signal and upload what they hear to www.phonesat.org.